Significant figures, a Hense production. Significant figures have to do with uncertainty in measurement. It's not like in math class. When I say significant figures, sometimes it's abbreviated sig figs, or some people say significant digits, and then you can say sig digs, whichever one you prefer. So numbers in science are different than in math. Numbers in science are usually based off of a measurement, based off of a tool. In math, you can kind of be as precise as you want. You can write down everything that the calculator says, or you round to whatever the teacher tells you to round to the hundredth place or the 10,000th mark. Or you can use that little line above the last digit to show that it's repeating. If it's 3.77777, you just write 3.7 and repeating. What we're saying in science is that you cannot be that accurate or that precise. You have to describe exactly how precise and accurate you are with your measurements. So it has to do with accuracy and precision of the tool that you're using. And it kind of has to show a reference to the human and how you observed it. So you can only be as certain in your measurement as the tool will allow you to be. So really precise tools, i.e. with more graduation marks, might be able to tell you a much different number than you would in math. So it has to do with certainty and uncertainty. So let's say I'm having a party and I say, all right, party starts, I don't know, 5-ish. That means I really can't blame anybody if you show up at 4:30 or 5:30 or even 6. But you might be really upset with me if you show up at 4:45 and I haven't gotten any entertainment. There's no DJ, I don't have any food out, nothing's ready. Or if you come at 5:30 and all the food is gone. I said 5-ish. That wasn't very precise. So I can't blame people for not coming at the right time. So scientists observe a measurement and record all the significant figures, and that lets everybody reading that measurement know exactly what kind of tool was used. So all certain digits have to do with the levels of graduation or tick marks there are on the tool, and you always record one additional uncertain digit. And the uncertain digit is the observed one. Let's say that I am measuring something in inches and it's not on the 11-inch line and it's not quite on the 12-inch line, it's in between. I get to record where I observed it, where I saw it. Was it halfway? Was it a little bit past 11? So that's the level of uncertainty, and there are no tick marks for that. So you record all the certain digits plus one uncertain digit. Let's see how it works if you're looking at this pencil, and I'm going to show you with different types of tools with different levels of precision so you can see how the measurements differ in the way that you record them as the tool gets more and more precise or less sucky. So let's look at the first tool. Let's say I wanted to measure it, and this ruler in centimeters kind of sucks. It only has a tick mark every 10 centimeters. So if I draw an imaginary line with my eye as to where the end of the pencil is, I can only be certain that it didn't make it to 10. Well, I, as the observer, still get to write down where plus my one uncertain digit. I think it's around 9, so I would write 9 centimeters. That's as accurate as this tool would allow me to be with that pencil. Okay? I couldn't say 9.5. I couldn't say 9.0. No points, just the one uncertain digit. Now, if I got a better tool, so here, now it has graduations for the 10s, and it has graduations in the 1s. So I can be certain that it made it past 9, or at least to 9. So I'm certain about the 9. And then me as the observer, I get to add one uncertain digit. It looks not quite halfway between 9 and 10, so I'm not going to say 9.5, but I can say 9.4. So 9 is the certain one. The 0.4 is the uncertain digit. That's the one I observed. It was almost halfway. Well, what if I got an even better tool? So now it's got graduations on the 10s, it's got graduations on the 1s, and it's got graduations in the tenths of a centimeter. So that means I am certain that it made it to the 9 graduation tick mark. I am certain that it made it to the 0.4. And then it kind of looks like it's right on the 0.4. So what digit would I assign as my uncertain one, my guessed one, or my observed one, that would let everyone know that I saw it right on the 4? I still have to add a digit, so I use a 0. So if I thought it was right on 9.4, I have to put 9.40. That's 2 levels of certainty, right? And then 1 uncertain one. Can you count the sig figs just based off of a measurement? What I'm going to do is I'm going to put significant figures, and then I'm going to answer how many in that measurement are actually significant. So if you want to practice, feel free to pause and then play to see the answer after each one of these measurements. I have 120,000 feet in a measurement. How many sig figs do you think there are? This would be where you would pause. 2 significant figures. Let's look at another measurement. 1,090 milliliters. How many sig figs? 3 significant figures. Another measurement, 0.0730 seconds. How many sig figs? 3. Last one, 10.09 pounds. How many sig figs? 4 significant figures. Do you know what's going on here? Can you figure it out? If you went on the internet and just Googled how to identify significant figures, you will find a bevy of different types of rules and understandings and examples that different scientists and teachers have put out there. I've tried to gather all that information together and come up with a really simple 4-step flowchart that will kind of explain what's going on. So I'll take you through mine. If you can imagine bookends are used to pin books in together on a shelf so they don't topple over. My idea is we're going to identify the most significant and the least significant number in a measurement, and everything in between. All of those will be significant figures. So I'm going to teach you how to identify the most significant and the least significant, and you just count from that one to the least. This is how it works. To identify the most significant digit, you have to go to the leftmost number that is not a 0. So the leftmost non-zero number is always the most significant number. Next, you ask yourself, is there a decimal recorded in that measurement? If there is, that means that the least significant number is the rightmost, no matter what it is, even if it is a 0. Whatever it is, go all the way to the right, okay? And that's the least significant. If there is no decimal, that means it might be implied, but it's not written down. You have to see it written down. If there is no decimal, then it's the rightmost non-zero that is the least significant. So let's see it apply to these examples up here and see if you can make sure that I was right with each one of those 2, 3, 3, 4 sig figs for those measurements. In 120,000 feet, the leftmost non-zero is the 1. There is no decimal, so that means the rightmost non-zero would be the 2. So that's why there are 2 significant figures. For 1,090, the leftmost non-zero is the 1. And there is no decimal, so the rightmost non-zero is the 9. Okay? The 0 in between them counts, but the 0 after is just a placeholder. So that's why there's only 3 significant figures. In the next one, the leftmost non-zero. Okay? If you go all the way to the left, it's a 0. And then after that is a 0. So the leftmost non-zero is the 7. And since there is a decimal written, you go all the way to the right no matter what it is. And that's that 0. So there are 3 sig figs there. And for the last one, the leftmost non-zero is the 1. There is a decimal, go all the way to the right no matter what it is, even if it is a 0, which is the 9, and everything in between. So 4 significant figures. So that's how just by looking at a number in a measurement, you can figure out how many significant figures there are. Now, when you manipulate these significant figures in mathematical operations such as multiplication, division, and addition, subtraction, which you do with measurements in science, especially in a lab, it's important that you know what your answer should be rounded to. Remember, if your calculator kicks out 10.085213335, you don't have to raise your hand and ask a teacher, what should I round to? You, based off of the rules, will be able to figure out how precise your final answer can be. So for multiplication and division, there's a different rule than there is for addition and subtraction. If you have these measurements, 22 times 8.93 times 23.060, I forgot to write the centimeters. All you would do is you would type that into a calculator, and that's what your calculator would kick out. 4,530.3676 cubic centimeters. I cannot be that accurate. That's what the calculator says, but I can't be that accurate. It's kind of like you're only as strong on a team as your weakest player. You're only as strong in a chain as your weakest link. Well, you can only have a final answer of a measurement calculated that is as precise as the least precise measurement that contributed to it. So your answer is rounded to the least number of contributing significant figures. If you look at those three measurements, we have to figure out how many significant figures each one of them have, and the least significant figure measurement is going to limit our final answer, and that's what we'll round to. So in 22 centimeters, there's only 2 sig figs. In 8.93, there's 3, and in 23.060, remember I forgot centimeters, there's 5. So 2, 3, and 5. The answer my calculator gave me was what? 1, 2, 3, 4, 5, 9 significant figures long. We can't be that accurate. 2 is the least, so our answer is limited to 2. Now, if we're going to keep 2, we want to keep the most and the second most significant number. The rest we need to get rid of, but we still need to create a number that's that big. So I like the 4 and I like the 5, but I still need to represent a number that's as big as 4,530.3676. So what I use is numbers that don't count as significant numbers but are placeholders, zeros. So 4,500. The 3 wasn't enough to make us round up to 4,600. It's closer to 4,500 than 4,600. Now there's a different rule for addition and subtraction. So for addition and subtraction, let's say you have 80.66 plus 50 minutes plus 23.057 minutes. Your calculator boop, 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 says 153.717 minutes. We cannot be that accurate in our final answer, okay? The rule is your answer is rounded to the least number of contributing decimal places. Different rule now. So decimal places. Decimal places are how many spaces are there after the decimal? The tens place, the hundredths place, the thousandth place, and so on. So in 80.66, 2 decimal places. In 50, none. No decimal places. There's not even a decimal. And in the third one, there's 3. So we're limited to the least, which is 2. Which is none. So that means we can't go to any decimal places. But here we have a problem down here is that I like 153. I get to keep all of them, but I can't have any of those places after the decimal. If I'm going to chop them off and get rid of them, is 153.717 closer to 153 or closer to 154? The 7, the stuff I'm going to chop off and get rid of, as a last dying ditch effort, knocks the 3 up to a 4. So we round up to 154 minutes. Now, so far I've taught you how to identify significant figures, and I've taught you how to use those significant figures in mathematical operations to round. Now, what if I gave you a measurement? Could you figure out what the tool that was used to make that measurement? If you have understood this stuff, it should be pretty easy. If you look at 320 milliliters, was it from a really precise beaker like the one on the right, or is it from a really not so good one, only goes to the hundreds like the one on the left? How many sig figs do you see? Leftmost non-zero is the 3. There is no decimal. Rightmost non-zero is the 2. So there are 2 significant figures. But here's the deal. If those 2 significant figures were written down, that means one of them was at least uncertain. So 3 in the hundreds place is certain, so there's definitely gotta be graduations for the hundreds place. Both those beakers have graduations for the hundreds, so they're both in the running. But the 20, the 2 in the tens place was guessed. That was the uncertain one. That was the observed one. That means there aren't tick marks for it. So the right beaker is actually the left beaker, okay? Only certain in the hundreds, and then the 20 was observed and uncertain. Thanks for watching.